Hello everyone! Thank you for joining to watch our video What Algorithms? I hope it will answer lots of your questions about algorithms in general and clarify and conveniently aggregate the most important information about them in particular. Too many things to discuss, so let's move on with the first topic, different goals when developing algorithms. Algorithms are in the main focus of this few parts video. Algorithms are methods for solving problems in a broad sense. In a narrower sense, within the scope of modern computers and their model of computation, we can observe that the largest set of problems to be solved are actually to search for some meaningful information subset out of large preliminary collected initial data. Just to mention, for algorithm to be effective, initial data needs to be stored in appropriate effective way, sometimes even specifically designed for particular algorithm. We will talk about what to consider effective later in this video. Data structure is a method to store information and is a very important term when we will be talking about most of algorithms in this video. We started discussing data structures in the other video of our portal with overview and basic examples. My recommendation is to watch that video first. Now we will dive deeper with a little bit more complex structures helpful to solve tasks by our algorithms. So what is this video about? We will be focusing on searching problems to be solved using computers by methods called algorithms. We'll list some real-world searching problems and discuss what algorithms and supported data structures, if needed, could solve them. Different approaches and goals can be used when developing algorithm to solve a problem, and it depends on who needs to develop new algorithm or maybe just learn existing algorithm. If you are just student learning particular programming language, then your focus most probably is mainly on capabilities and syntax of a language, to understand what can be expressed and solved by this language itself. Of course, learning language by memorizing list of available operations provided by particular language is boring and not so effective. Practice is very important. Therefore, meaningful technical activity in form of tasks to be solved while learning is underneath your practice, and student picks interesting tasks to learn a language. Algorithms to develop exist here as a side effect. Student may not be fully focused on correct answer to the overall task or correct answers to different input data, but rather to be sure his/her program works without mistakes and provides proper answer at least for particular given input data. Let's think with an analogical example not from a computer world. Remember, algorithms in general are not only to solve computer world problems. For example, you want to learn, does anyone capable to pick up ripened blueberries from the bushes? You focused on capabilities. Of course, it's always good to feed your curiosity with real task. So you come up with such a task, for example, to pick up blueberries into a small basket. If you can do that, you can consequently make an outcome that someone, maybe you, is capable to pick up blueberries, and you learn wanted capabilities. Your algorithm may consist of several steps. For example, someone needs to have good vision and to determine how blueberry bush looks like, not to mix it with strawberry or raspberry or any poisoned blueberry looks like or any other bush. Someone needs to know that bushes consist of branches, possibly carrying blueberries. Don't mix blueberries with leaves. Someone needs to know how to consider blueberry as ripen by checking berry's color. Someone needs to know what is basket and have this basket available. Someone needs to have arms. Take berry from a branch and put it into a basket. Someone needs to check when basket is full of berries to stop harvesting and consider task is done. If you made algorithm working, delivering task eventually showing it can be done, then you learned all capabilities on the way, which we have just mentioned in each step of our algorithm. And you made it in a fun, meaningful, purposeful way. Same way with programming language. You can learn types of data allowed to be used by a language. Instead of bushes, baskets, and berries, you will have arrays, sets, integers, and other data types, which we started discussing in data structure videos. You can learn programming languages operations which you can apply to your data. Analogically to pick from a bush and put in a basket, you can have operation to subtract existing data and to add some new data to your set or array of certain data type. You can check that particular computer is capable to fulfill the algorithm's task. analogically to have vision and arms to find input value and results somewhere in computer's memory. While student writes software program to solve a task, he/she rehearses and remembers language capabilities and how such capabilities are expressed in properly written commands. That was about students' task of learning syntax and capabilities of a language, where algorithms are used as a side effect. Moving out from students, on the contrary, software developers and potential candidates for this role during interview are not focused mainly on programming language syntax. They assumingly are proficient, but rather on a given task. So they want first of all to develop, no doubt, always stably working solution. In the previous example, student gives tasks to himself, and it's usually easier to set specific convenient input data values and size. For example, just one bush to work with and just one basket. Developer usually cannot predict all possible input data values and how large this input data can be. In lots of cases, it's unknown prior task to be started. But regardless of amount of input data or incoming values, algorithm should always provide a correct output answer to a given problem. Let's again think analogically. You need to develop always working algorithm to pick up all ripening blueberries from a whole field or even several fields. At the time of developing algorithm, you have no idea how large field is to be and how many bushes to take care of. Let me now introduce term which is used in software developing industry: brute force algorithm. In simple words, brute force is a method of solving tasks to check all possible input data or data combinations during so-called exhaustive search for a solution. Main idea behind it is not to miss even any single possible input data combination, which may have impact on overall result. Applying brute force approach to our task, logically you can conclude that once you can check all bushes in a field and pick up all ripened blueberries from each of a bush, you can consider your task is perfectly done, always bringing proper result of initial task. Logic is totally fine. Our algorithm is not using any conditions and fine-tuning. It's not analyzing that certain small young bushes planted, for example, 4 months ago, physically cannot carry berries. We're just checking each bush, one after another, checking all branches, and finally concluding on the way that some bushes don't carry berries. How fast you solve your task is not so important when you apply brute force approach, but such approach potentially gives you always working solution based on fact that no part of input data is missing. Not to miss any input data for our blueberry task, we just need to be sure to visit every bush. If you are familiar with agriculture and put your algorithm within a scope of farm-raised blueberries, you can try to make your visit every bush task easier by seeing some repeated patterns and structures. You can consider every blueberry field consisting of rows of bushes, while each row can have the same amount of bushes. Let's have the same for simplicity. So your algorithm can calculate number of rows and number of bushes in a row at the beginning, and then make repeated actions, check bushes in the first row, then in the second row, and so on till the last row. While checking bushes within each row, there are also repeated actions, checking bush number 1, then bush number 2, and so on till the last bush. Visiting each bush is one subtask, while checking all branches and picking up berries is a separate task, out of scope for now, which should be similar and therefore applicable to any blueberry bush. If you plan to use this algorithm on any other blueberry farm, it still should be working, bushes will be the same, number of rows and bushes in a row might be different though, but algorithm can calculate it at the beginning. In a software developing, your program analogically may have similar structured data with rows and columns analogies, with capability to be of a different size, depending on incoming input data. That was about software developer task of making always working algorithm regardless of amount of incoming data and input values. An algorithm is said to be correct if, for every input data set, it provides correct output. Brute force algorithms can help to make algorithm always working by not missing any single input data. To clarify, brute force is not the only way to solve tasks, and not necessarily developers use brute force solutions. Moving from developers' goals. After developers, we have clients. Client, who usually orders software from external companies, wants to solve problems efficiently. Key point, Same problem usually can be properly solved different ways, using different algorithms. And all such algorithms can provide working solutions. We will see such examples later in this video. Imagine if algorithm from a first software company can solve the same problem 100 times faster than algorithm from a second software company, with all other software characteristics to be the same. Can you guess which algorithm client will choose? Optimization and consequently efficiency of an algorithm is in main focus for client. Number one factor is a task completion speed. For example, one company developed a machine with mechanical innovative way of shaking blueberry bush for, let's say, 10 seconds, so all ripened berries are falling into a large basket under the bush. That would speed up harvesting if compared to manual branch by branch, berry by berry picking up, which may eat, for example, up to 10 minutes instead of 10 seconds. So economy on each bush will be more than 9 minutes. What if you have 100 bushes filled? More than 900 minutes economy. The larger the size of input data, the more time economy could be seen. Another optimization example. Sometimes algorithm developers can figure out certain possible conditions which may allow to optimize algorithm even more. For example, if we know that bushes under certain age cannot give berries, we can mark such bushes and even whole rows of bushes as young. Then in time of executing algorithm, we can skip such bushes and even whole rows from searching. So instead of our brute force algorithm to check every bush on a field, we found more intelligent way to speed up execution by skipping some marked input data. Both algorithms will give you the same amount of berries picked, but brute force algorithm will be checking and spending time on each young bush, which can be potentially skipped. These were just a couple of examples to show logic of optimization of algorithms to make them being executed faster. Everything comes with a price. Brute force algorithms are intuitively easier to understand. Write a code for them and consequently read such a code. Because you just check all input data, one item after another, applying the same logic on each step. When optimizing or coming up with totally new, faster algorithm for the same problem, readability and understanding usually is not so intuitive because of taking care of some conditions, possible input-output data restrictions, certain tricky assumptions, and it requires some efforts to explain and understand them. We will work on explanations of major effective, fast-working algorithms later in this video. Not only speed of algorithm execution might be in focus. Another factor to consider is memory of a computer. If you take a relatively small basket to pick up all berries from a field, you can figure out quickly that it might be not enough and you can fill it after a couple of bushes, while still having almost the whole field to go. It's tempting to bring pile of super large baskets with the size of swimming pool to ensure you have enough storage. But you need to understand that taking too large size may end up with filling only a small portion of it during algorithm execution. And analogically thinking, reserving large basket size means for computer that you take a large piece of a computer memory. Memory is not unlimited resource, so it's not only can be underloaded or even almost not utilized when you reserve too large pieces of it, but also if you have lots of input data and improperly reserve a large amount of memory, you even made up taking all of computer memory. So it's another item to think about. We will not be focused much about memory in this video though, but please keep in mind there is a need to think about it when designing algorithms. Do not allocate chunk of memory for 1 million items, if in most cases you will use just few items. Don't use water of a whole swimming pool for just quick rinsing of hands. That was about clients and their needs for effective algorithms. Good developers and job candidates keep clients and potential employers' needs in mind to prepare a working and also effective solution. From clients' needs, moving next. Listeners of this video in particular, and curious minds in general, want to understand how algorithms work, including efficient algorithms. Conditions, optimizations taken care by algorithms, especially scientific-grade algorithms, have lots of assumptions and make writing software code not so obvious and easy. Reading such code to understand might be even more difficult task. We will unleash our imagination and find simple explanations for algorithms looking difficult later in this video. Wrapping up different approaches and goals when developing algorithms. Students may want to learn programming language syntax and use algorithms as a side effect, just to practice some solution. All developers and interview candidates need to have always working algorithm, regardless of input data. Great developers and candidates who follow clients' needs, and clients as well, they want to have efficient algorithms. Whoever watches this video and curious minds want to understand how algorithms work. Let's move on and dive deeper. Let's talk about time. You still can purchase old-school wristwatches with clock hands, even though more and more smartwatches and other time-tracking devices are on the market. These clock hands allow you to visualize how time flies. Some watches have hand to show seconds. Such hand turns clockwise a little bit to the next position every second. Each step or turn requires exactly 1 second to be done. You need to have 60 steps of this second clock hand to conclude that 1 minute is gone. So another minute clock hand moves to the next position, and so on. Accurate visualization of time moving forward. Let's say you have some physical exercise task from your trainer in a gym to make a block of 10 steps followed by 10 squats and repeat this block 2 times. Such task sounds like an algorithm, step-by-step procedure to solve a problem. Train your legs and heart muscles at certain intensity. Each single operation, like step or squat, or anything else trainer could add later, can be done at its time. We can name it cost of operation. For simplicity, let's assume 1 step can be done at a cost of 1 second, 1 full down-up squat at a cost of 2 seconds. How long does it take to execute your gym task? Visualize it on our old-school wristwatch. 1 second per each step, 10 seconds for all 10 steps, and analogically 20 seconds for 10 squats, 2 seconds each. Since you need to repeat 2 blocks, each block at a cost of 30 seconds, the total execution time will be 60 seconds. Over the time, trainer can increase intensity of your training and can ask to repeat more blocks of steps and squats. The overall task completion time will be increased accordingly. What we have just done to calculate overall algorithm's time execution. We summed up times of all operations of our algorithm. 1 second for each step, 2 seconds for each squat. Math multiplication was discovered to simplify our lives. Instead of brute force sum up of all single operations times, one after another, we can determine how many different operations, like steps, squats, you have within your algorithm. Multiply cost of each operation on its frequency. Frequency in our context means how many times, how often this operation was executed. For example, overall task had just 2 operations, repeated over the time. The first operation, total 20 steps, frequency of steps, multiplying by 1 second, the cost of step. 20 seconds in total for all steps operations to execute. Similarly, total 20 squats, frequency multiplied by 2 seconds, the cost of squat. And we have total 40 seconds to execute all squats. Our algorithm doesn't have any other operations consuming extra time. So algorithm's overall execution time is 20 seconds for steps and 40 seconds for squats, totaling 60 seconds. Returning to computers, can we estimate how long does it take to execute program? Actually, very similar accurate mathematical model available for checking running time of a computer algorithm. Some simple algorithms may consist of just few types of operations. For example, to calculate value based on input parameters and mathematical formula. Computer usually just executes each operation consequently one after another. And each step takes certain time, cost of operation, which can be measured. We can also visualize overall running time of a program on imaginary wrist-like watch. But scale of your watch should be calibrated by nanoseconds instead of seconds. There are billion nanoseconds in each second, so humans cannot feel nanoseconds by our sense of perception. On a particular computer, for example MacBook Pro 2.2 GHz with 2 GB RAM, it was measured for particular program that integer add operation takes 2.9 nanoseconds. Next command, integer multiply, takes 2.4 nanoseconds. Floating point divide takes 13.5 nanoseconds, and so on. So you can calculate total running time of your program from start to finish by sum up cost of all executed operations, conveniently using math and aggregating by each operation, multiplying cost by frequency of operation, like we did for gym training exercise task. But instead of steps and squats from our analogical example, computer operations are a read value, integer add, integer multiply, and so on. Total running time of an algorithm can be, for example, 2.1 nanoseconds multiplied by 100 if 100 integer add operations to be executed, plus 2.4 nanoseconds multiplied by 50 if 50 integer multiply operations to be, and so on. To note, such costs of each operation depend on a computer. Some computers are obviously faster than others. The same program code can be executed slower or faster on another machine. Another factor, costs of operations may depend on programming language and its compiler or interpreter. Does execution time for our task depend on cost of operations only? Of course not. We have forgot frequency of operations, how many of them or how often will be done while algorithm is running. Imagine factory-grade program running somewhere on a big IT company, which executes millions, billions of operations instead of just few. If cost of operations depend on computer and programming language, frequency of operations depend on two other things. First thing, frequency depends on input data values and mostly size or number of parameters. Remember, algorithm prepared upfront to handle input data of any size. From our previous analogical examples, we do not know how large is a blueberry field before starting execution, or we don't know how many blocks of steps squats gym trainer will ask us to do today. Second very important thing, frequency of operations also depends on algorithm. How smart and optimal is it? Brute force solution will take more execution steps compared to optimized way of solving problems. Will you check every blueberry bush or can skip some? Remember that each bush check may have multiple steps, each at its cost. Do you plan to handle every bush manually, branch by branch, or automatically, checking the whole bush? What if gym trainer can share with you different algorithm to achieve the same intensity of muscles practicing? Instead of 10 slow steps, you can do just 3 fast jumps. We will pay attention in this video how smart algorithms can reduce frequency of operations to speed up overall task execution. Let's wrap up. Accurate mathematical model to calculate running time of algorithm consists of few steps. Finding different operations, multiplying cost of each operation by frequency of this operation and sum it up. Very important to remember, operation cost depends on computer and programming language, system-dependent factor. Operation frequency depends on input data values and size, and how well algorithm is optimized, system-independent factors. What is surprising, it turned out that optimized algorithms have greater impact on runtime than speed of the computer. We will see later that even supercomputer, which is tens of thousands times faster than your home computer, can spend weeks with non-optimized algorithm even with not so large input data size. What we discussed so far? Just 2 topics. What is algorithm? Different goals when developing algorithms. We mentioned students, developers, and developer job candidates, clients and great experienced developers, or just listeners, curious minds. They all may have different goals. And second topic was about mathematical model of calculating algorithm execution time, which in short is summary for multiplication of costs of each operation on its frequency. Frequencies of operations rely on system-independent factors, input data size and algorithm. And better algorithms running on a home computer could outperform worse algorithms for the same task running on a supercomputer. Let's move to fine-tuning and continue in the second part of the video.